Guys, this section of the laboratory or the lecture module is going to be called Learning the Language. So we've talked about routes of exposure, and now we're going to have to go through and talk about maybe different resources that you have as an employee or as a student that's basically at your fingertips. Most of them are, at least. And we can kind of refer to those to figure out how to limit our exposure routes. So just like before, I want to start off with an incident. And here we have one. A technician was carrying out a procedure with boiling acetic acid as the solvent. Boiling acetic acid, that stuff is pretty strong. And if it's boiling, then that means noxious fumes are probably being given off. So imagine smelling vinegar, but imagine smelling vinegar like 10 times as much, because this is concentrated acetic acid here, not a weakened down version like vinegar might be at your house. She needed to add some additional solvent, so she obtained what she thought was a bottle of acetic acid and added some of the contents to the flask. Now, here's the problem with that sentence. She obtained what she thought was acetic acid, right? That's a weird word, thought. So it maybe wants us to believe that there was no label on the bottle. And because of that, she just assumed that it was acetic acid when it really wasn't. Immediately, there was a loud noise, and the boiling solution blew out, hitting the ceiling. A cloud of brownish fumes were noticed after the eruption, and upon checking the bottle, the technician realized that she had actually picked up a bottle of nitric acid instead of acetic acid. So, that kind of puts an answer to our question. Yeah, it did have a label. And yes, it was properly labeled, but she didn't double check the label. And because of that, this nasty explosion happened because of it. Because the technician was wearing the correct PPE, there was no injury. So that's good news. Nothing happened because of it, because she did put safety precautions in play. However, there was an incident that happened, and this incident could have been prevented if she just double checked the label that was on that bottle of nitric acid. This would have never happened. So some things that we can take away from this incident is, number one, double check your labels. Make sure that you are correctly reading the information that's on the label itself. And we've talked a little bit about labeling in the previous section of the module. Number two, always wear the correct PPE. So that means she probably had gloves, she had a lab coat, she had closed-toed shoes, she had pants, all of her skin, or most of it at least, was covered up, she had goggles. And number three, always think about what could happen. Now, this is kind of weird, because why was nitric acid out in the first place? Was it out on the shelf for someone to use? And you probably could not go in and just assume, well, what if I mix this nitric acid with acetic acid? What would happen? Right? So these are some of the things that we're going to have to kind of do and kind of react to on the spur of the moment. But good news, she wasn't hurt. So this leads me to the point of discussion that we're just going to sit down and kind of talk about. And you're probably wondering this anyway. But you need to understand that there's hundreds of chemicals that you might be exposed to on a daily based environment, right? Depending on what type of lab that you're working for, there could be hundreds of chemicals that's going to be basically at your disposal. So you have to make sure that you understand kind of the basics for pretty much everything that's in the lab that you work with. So how do you know the specifics of each one, right? When I get hired for a laboratory company, does that mean that they're going to give me a list of these 100 chemicals and I'm going to have to figure out how to handle them all at once and what I should do in case something happens, like a spill or a reaction with them? And the answer is no. This stuff takes time, right? It's going to take time for you to understand how to work with these chemicals, how to handle the chemicals, and how to protect yourself from the chemical, okay? So don't worry about it. That's the answer. The same thing is going to happen in an academic lab. Don't worry about what we're using in the lab. You will start to pick up these safety techniques. You will start to pick up what you should do in case something happens as you go along in our program and as you work longer and longer and longer for the employer. Now, because there are chemicals, there could be hazards that are associated with these chemicals. And there's a couple of things that I need to make sure that I feel comfortable with knowing, at least information-wise, on these chemicals before I work with them. All right, so the number one thing, of course, is toxicity. Okay, I want to know how toxic they are. If I'm working with these chemicals in a laboratory and I spill them on my hand, or I breathe in the fume, or if I use them in some type of reaction, I want to know, are they going to poison me? Yes or no? And if they will, what is my exposure limit? Right? Is it one of those things that if I just take a breath of it, then I'm going to go to the hospital? Or is it one of those things that I can really just almost take a bath in before it becomes toxic? Those are the things that I'm going to have to kind of figure out as I work with these chemicals, as they come up in my daily routines. The next one is flammability. This, of course, means, does it catch on fire, right? Does it catch on fire, or can it cause something else to catch on fire very easily? What is the flammability rate of this thing? Should I keep it near an open flame? Or should I completely take all open flames out of the room and not worry about them anymore and make sure that there is no chance of this stuff from catching flame? That's the kind of thing I'm going to have to think about when I work with some of these chemicals, because sometimes they're going to be a bothersome and a nuisance for us. Next is reactivity. Reactivity is pretty important because that's basically how does it react with something else. So if I'm using it in a laboratory, I want to make sure that it's not too sensitive to other things. And if it is going to be sensitive to something else, I need to know what that stuff is going to be. That way I don't cross paths between those two chemicals. I can keep them separated. They will never come in contact with each other, and I'm safe, and my coworkers are safe, and the people that might be taking the class with me will be safe. So reactivity is going to be another factor that I'm going to have to look at when it concerns all of these chemicals that we're working with in a laboratory. And then finally, the last one is corrosive. What's the corrosivity of the chemical that I'm using in the laboratory? So what does corrosive mean? Well, we'll talk about that in a little bit later, but you can kind of think of metal and think of it rusting, at least for now. So how does it react with other things like that? What kind of products is it making? Is it destroying stuff that it's basically coming in contact with it? So the question is, if these four things are what I want to watch out for: toxicity, flammability, reactivity, and corrosiveness, where do I find the information? Can I use an online resource? Is there a book that I need to get in a laboratory space? Is there something that I can do maybe at home before I go into those laboratory spaces and do a little bit of homework to figure out how I should handle it, or what should I watch out for? And not only how do I find it, but how is it organized? Is it alphabetical order, or is it listed in order of something else? So these are the things that we're going to have to walk through, so that way you feel very comfortable in knowing where to find the information that you have to have before you safely go into a laboratory and work with some of these chemicals. All right, so we're going to talk a little bit about basics for a minute, and the very first thing that I want to talk about is naming. Because if you're going to find a resource, if you're going to find a literature or a textbook or some kind of reference, it's probably going to be listed as far as names of chemicals go. That's going to be the easiest way for some of this information to be organized. So in chemistry and in pretty much any laboratory, when we refer to naming, what we're referring to is nomenclature. And nomenclature is very important. There's actually two pieces of nomenclature systems. There's one for inorganic material, and there's another one for organic material. Organic material is not the organic that you would see at the grocery store on your fresh produce and vegetables. That is not organic, all right? That organic basically means no pesticides, no herbicides, and that kind of thing. Okay, naturally grown. Organic for a laboratory is completely different. That is not what it means. They're two totally different definitions. For organic in a laboratory, what we're talking about is a carbon-based structure. So let me give you an example. Organic would be something like glucose. All right, that's carbon-based. I see carbon making up the backbone of that structure quite a bit. There's a lot of them. There's a little bit of hydrogen thrown in, a little bit of oxygen thrown in, but that's about it. This is a carbon-based structure. Well, inorganic would be something like salt, NaCl. That's not carbon-based. There's no carbon that's present there, right? I see sodium, I see chlorine, but never do I see carbon. All right, so in these two systems, inorganic and organic, we're going to name them a different way. And I'm not going to go through the rules of the nomenclature. General chemistry, such as chemistry 151 and 152 at the college, they will go into inorganic nomenclature. How should you name things, and what are the rules in order to name them? When you get to the Chemistry 251 and 252 series, which is the organics, well, that's where the organic nomenclature comes into play. This is a totally different systematic rule set. I name them differently. There's different rules that I follow, and it's a pain. Half of organic chemistry is just learning how to name things. That's all that it is. And what you're going to find out is that in either one of these routes, organic or in the inorganic, the problem is that there are multiple names that can be used for some of these. When I talk about multiple names, some can have 2 names. Some chemicals can have 4 names. Some chemicals can have 20 names. It just depends on the structure itself. And that can be an issue for us. Out of these multiple names, there's 2 typically that we always see. One is going to be an IUPAC name, and the other one is going to be a common name. Instead of the word IUPAC, some people use the word systematic. A systematic name and a common name. Systematic basically means there's a system in place. There's a set of rules that you go by, number 1, number 2, number 3, number 4, in order to name it. That's why they use systematic, because that's what IUPAC has done. What does IUPAC stand for? Well, it stands for International Union of Pure and Applied Chemistry. It's basically a panel of a bunch of people with PhDs that think that they're super smart, and they sit down, and part of their job is to go through and figure out how to name compounds and give you rules on what they want you to do, because again, they're smarter than you are. Give me a break, people. I think it's just a way to justify a job. But I will say that these systematic names are pretty important. It does give a little bit of order to the chaos that can happen in a laboratory environment. Okay? So as long as you learn the basic rules, then you're good. And I don't have a problem with IUPAC. What I do have a problem with is that sometimes IUPAC will make a series of rules, number 1, number 2, number 3, number 4, and they'll say, this is what we want you to follow, number 1, number 2, number 3, number 4. We learn that way, 1, 2, 3, 4. We name it the way that they tell us, 1, 2, 3, 4, and then they're going to turn around and change the rules on us sometimes. And they'll say, well, it works, but there's some exceptions, and here are some of the exceptions. No. That's not how this should happen. There should not be any exceptions. If you're going to do systematic name, you should give me a system, a set of rules, and that set of rules should not change, and it shouldn't modify. But that's not how real life works. So IUPAC's great. It works most of the time, but keep in mind that it's not 100% reliable. Common names. Common names are typically coming from the old school name. That's how I'm going to refer to it. Hundreds of years ago, these compounds might be used in a laboratory, and they were called a specific name. And then over time, we have adapted those names or adopted those names in making sure that this is what we will actually call that chemical from here on out. And it's just something that was commonly done back in the day. So let me give you an example. For instance, NH3. NH3 is not called nitrogen trihalide or hydrogen or hydride. Sorry. It's not called nitrogen trihydride. What we call this is ammonia. IUPAC would want us to use this name, but we do not use that name. Instead, we use ammonia because that's really what it was called when it was first used back in the day, many years ago before IUPAC came along. The same kind of thing's going to happen with H2O. We're not going to call this dihydrogen monoxide because that would actually follow IUPAC rules. Instead, we call this stuff water. Water is a common name. That's what we've always used for that chemical because it is a chemical. There's no difference between that and anything else that you use in a lab. But that was the adopted name for that particular type of substance. So we do have common names and we have IUPAC names. There could be one IUPAC, one common, and that's it. There could be one IUPAC and 20 common names. So what do we use? So what we have been told to share with you is that when we talk about naming and looking compounds up in a reference book, we should encourage you by default to go and look at the IUPAC or systematic name. So we're going to have to learn some of the IUPACs, and that's not the purpose of this course. That's the purpose of general chemistry, and that's the purpose of organic chemistry. But IUPAC is a name that we should focus on because that's going to tremendously help us out when we go and look compounds up in reference literature to figure out the good things and the bad things on them.